We have two equations now relating this number of states. And now you can say, oh, okay, so I look at the k line, and I look at the little piece dk and say, oh, how many states were there with zero potential? Some number, first blackboard. How many states are there now with some potential? Some other number. It has changed. For every, because these two equations, dn for equal dk, dn is not equal to dn prime. In one case, the energy levels or the momentum levels are more compressed or more separated, but whatever it is, whatever the sign is, there's a little discrepancy. So both of them are giving me the total number of positive energy states in a little decay. So if I take the difference, I will get some information. So I would say the following. If I want to calculate the number of positive energy solutions, and now I think the following. I take the potential V equals 0 and slowly but surely deepen it, push it, and do things, and create the potential V of x, slowly, slow the formation. In this process, I can look at a little interval dk and tell how many states, positive energy states, I lost. So if, for example, dn is bigger than dn prime, dn equals 5 and dn prime is equal to 3, I started with 5 positive energy states in this little interval, and by the time I changed the potential, I ended up with 3, so I lost 2. So let me write here the number of positive energy solutions lost in the interval dk as the potential is turned on is dn, the original number, minus dn prime. If that's positive, I've lost states. If it's negative, I gain states, positive energy states. And this number, we can calculate the difference. This is minus 1 over pi d delta dk dk. So I'll put it here. All right. Well, we're not far. Well, this is what you lost, the number of positive energy states that you lost in little decay. To see how many positive energy states you lost overall, you must integrate over all the decays and see how much you lost in every little piece. So the number of positive energy solutions lost, not in decay, but lost as the potential is turned on is equal to the integral over k from 0 to infinity of minus 1 over pi d delta dk is the integral of that expression, of that right-hand side. But this is a total derivative. So this is minus 1 over pi delta of k evaluated between infinity and 0. And therefore, the number of states lost is 1 over pi, because of the sign, delta of 0 minus delta of infinity. So we're almost there. This is the number of positive energy solutions lost. Now, I want to emphasize that the situation is quite interesting. Let me make a little drawing here. So suppose here is the case where you have the potential equal to 0, and here is energy equal to 0. Then you have all these states. Now, even though we've put the wall allows us to count the states, but there's still going to be an infinite number of states. The infinite square well has an infinite number of states. So that thing really continues. But what happens by the time v is different from 0? Here is the E equals 0 line. And here's the E equals 0 line. As we discussed, as you change the potential slowly, these are going to shift a little, and some are going to go down here, are going to become bound states. There are going to be a number of bound states. And bound states. Number of bound states. Called n. And then there's going to be still substates here that also go to infinity. So you cannot quite say so easily, well, the number of states here minus the number of states here is the number lost. That's not true, because that's infinite, and subtracting infinities is bad. But you know that you've lost a finite number of positive energy solutions. So as you track here, the number of states must go into each other. And therefore, if these 4 states are now here, before they were here, and those were the positive energy solutions that were lost. In going from here to here, you lost positive energy solutions. You lost a finite number of positive energy solutions. Even though there's infinite here and infinite here, you lost some. And you did that by keeping track at any place how much you lost. And therefore, the states lost are never really lost. They are the ones that became the bound states here. So the positive energy states that got lost are the bound states. So the number of bound states is equal to the number of positive energy solutions, because there are no lost states. So this is equal to the number of bound states. Because there are overall no lost states.